Heat is energy in motion, or energy that flows within matter due to a temperature difference. Hence a given mass of matter that is at a given temperature does not contain heat. Rather, it has a certain amount of energy stored in it due to its higher temperature with respect to its surrounding. Energy that flows out of, or into, any given mass of matter is called heat. For example, we can say that the shown metal screw has a certain amount of internal energy, EI, stored in it. If the screw is at a higher temperature than the shown nut, then if the nut comes in contact with the screw, heat flows from the screw to the nut until they both reach the same and equilibrium temperature. The heat flow stops once the temperatures of both the screw and the nut become the same. Heat is denoted by capital Q, and has units of joules. Energy is denoted by capital E, and also has units of joules. Joules is written as capital J, and is equal to Newton times meter. We conduct an experiment, in which we place a certain mass of liquid, within an insulated container. The container has an electric heating coil inserted into it. The thermometer is used to measure the liquid temperature, which is initially at 293 degrees Kelvin. The stopwatch is used to measure the time it takes for the water temperature to increase by 10 degrees Kelvin to 303 degrees Kelvin. When the heater is turned on, the amount of energy, E, supplied to the liquid in joules is equal to the flow rate of electric energy through the heater, E in watts, times the time T is measured by the stopwatch in seconds. Assuming all the electric energy supplied to the heater is converted into heat that is absorbed by the liquid, we can write that the heat flow to the liquid, or Q, is equal to E times T. We can hence calculate the amount of energy required to raise the temperature of the liquid by 10 degrees Kelvin, by simply turning on the heater, and then recording the time it takes for the liquid's temperature to increase to 303 degrees Kelvin. By multiplying the heater wattage setting, which is 500 watts or Newton meters per second, by that time, which is 1 minute, or 60 seconds, we get the amount of heat that flows into the liquid, which is 500 times 60, or 30000 joules. In the initial run, we obtained the amount of heat that must flow into the liquid to increase its temperature by 10 degrees Kelvin. Now we can vary some of the parameters of the experiment and see how they affect that amount of heat. We will conduct 3 additional experiments. In the first one we will study how Q changes with the amount of mass m of the liquid, by doubling the mass of liquid within the tank, while keeping the temperature difference constant. In the second experiment, we will study how Q changes with the temperature difference delta T, by doubling the temperature rise to 20 degrees Kelvin instead of 10 as in the original experiment, while keeping the mass of liquid constant. Finally, in the third experiment, we will keep both the temperature difference and the mass constant, but we will vary the type of liquid within the container. In the first experiment, we double the amount of liquid that is within the container, and run the experiment again. We find that we need to double the amount of heat that is added to the liquid, by doubling the amount of time the heater is left on to 2 minutes, in order to get the same temperature rise of 10 degrees Kelvin. We conclude that we need twice the amount of heat to raise the temperature of double the amount of mass by the same amount. Hence Q is directly proportional to m. In the next experiment, we measure the amount of heat required to raise the temperature of the liquid, by double the amount of the first experiment, or 20 degrees Kelvin. We find that we need to run the heater for 2 minutes, in order to provide twice the amount of heat to raise the temperature of the liquid by 20 degrees Kelvin instead of 10 degrees Kelvin. Hence Q is directly proportional to delta T. Finally, we can repeat this experiment with various types of liquids, while holding the mass and temperature rise constant. We conclude that the actual numerical value of Q is dependent on the type of liquid that is used. Finally, using the previous observations, we can write an equation for Q as being equal to the mass of the liquid m in kilograms, times a proportionality constant Cp which depends on the liquid that is used, times the temperature difference delta T in Kelvin. The proportionality constant is called the specific heat, and it is a material property of the substance that we use for the experiment. We can write it as shown. The specific heat has units of joule per kilogram Kelvin. In differential form, the previous equation can be written as dQ is equal to mCp dt. In the shown equation that was derived in the previous section, Q is the amount of heat that is needed to change the temperature of a certain mass of matter m, with a specific heat Cp from a temperature of T1 to a temperature T2. If heat is being added to that mass of substance, then Q and the temperature difference are both positive. If heat is being removed from that mass of substance, then Q and the temperature difference are both negative. The term m times Cp can be replaced by the variable capital C, which is known as the heat capacity, and has units of joule per Kelvin. Unlike the specific heat, which is a material property that is associated with a given substance, the heat capacity is a property that is associated with an object. The two shown objects that are both made out of iron have the same specific heat, which is that of iron. Yet they would have different heat capacities if they had different masses. We can even calculate the effective heat capacity of non-uniform objects that are made up of a number of substances. The effective heat capacity of a non-uniform object is equal to the summation of the mass times the specific heat of all the substances that are present in the object. Calorimetry is an experimental technique that is used to measure the specific heat of substances, or the heat that is generated by a chemical reaction, or the heat associated with a phase change, such as ice changing into water. Shown here is the world's first ice calorimeter, used to measure the heat of various chemical reactions. The procedure for finding the specific heat of a substance begins by heating the sample of the material whose specific heat we wish to measure, and then recording its mass and temperature. The sample is then dropped into a well-insulated tank that contains the known mass of water that is at an initial known temperature. Once the sample, whose temperature should initially be higher than the temperature of the water that is in the tank, comes into contact with the water, heat is transferred from the sample to the water until both of them come to a steady-state equilibrium temperature that we call T-final. We can then use the conservation of energy principle to calculate the specific heat of the sample. Using the conservation of energy principle, assuming our system that includes both the water and the sample is perfectly insulated, then the total energy of the system should remain constant. Hence the energy that is absorbed by the water to raise its temperature to the equilibrium temperature must be exactly equal to the energy that is released by the sample to lower its temperature to the equilibrium temperature. Hence the summation of the mass m times the specific heat Cp times the change in temperature delta T for all the components of the system must be equal to 0. Since we only have two substances in our system, namely the water and the sample, we can drop the summation sign, and replace it with the addition of the change in energy terms for the water, and the change in energy terms for the sample. In the shown equation, we have replaced delta T water by T final minus T water, and delta T sample by T final minus T sample, where T water is the initial temperature of the water, T sample is the initial temperature of the sample before it is dropped into the water, and T final is the final equilibrium temperature of both the water and the sample. We can then equate the change in energy for the sample to the change in energy for the water. Finally, we can rearrange the terms of the equation and solve for the specific heat of the sample. An iron bolt that weighs 7 kilograms is dropped into a tank that contains 10 liters of water. The initial temperature of the iron bolt is 88.6 degrees Celsius, the initial water temperature is equal to 20 degrees Celsius, and the final equilibrium temperature is 25 degrees Celsius. If the specific heat of water is equal to 4186 joules per kilogram Kelvin, what is the specific heat of the iron bolt? We are given the following information. The mass of the sample is 7 kilograms. The volume of water is 10 liters, which is equal to 2.01 cubic meters. The specific heat of water is 4186 joules per kilogram Kelvin. The temperature of the sample starts at 88.6 degrees Celsius. The temperature of the water starts at 20 degrees Celsius. And the final temperature of the water and sample, after dropping the iron bolt into the water, is 25 degrees Celsius. we are asked to find the specific heat of the sample. First we calculate the mass of the water in the tank as the volume of the water times the density of the water, and we get 10 kilograms for the mass of the water. We then substitute the values of the variables into the equation for the sample's specific heat, and we get that the specific heat of the sample is equal to the mass of the water times the specific heat of water times the temperature change for the water over the mass of the sample times the temperature change for the sample. Evaluating this expression, we find that the specific heat of iron is equal to 470.1 joules per kilogram Kelvin. Notice how the specific heat of water is about 10 times larger than the specific heat of iron. Shown here is a table containing the specific heat values in SI units of some common gaseous, liquid and solid substances. Notice the high value of the specific heat of water as compared to most other substances. Living creatures that are almostly made from water are able to limit changes in their body temperatures due to water's high specific heat. This is due to the fact that it would take a loss or gain of a large amount of heat to change the body temperature of an organism whose mass is mostly made up of water.